Hello, Integrated Math 1. Welcome to lesson 2.3.2a. We're actually module 2 still, but we're on topic 3 now, and we're on lesson 2. And we're just doing the first half of it today. So we're just doing activities 2.1 and 2.2 today because it's kind of a lot that's going on in this. But this is my favorite way of solving linear systems. That's what we're doing today. So remember our scenario from the getting started activity, right? The whole comic gurus group, and we said the female group members outnumbered the male members by 34, that there was a total of 324 people in the group, right? Remember all this. We just did this together in class. So let's see if we can come up with an algebraic strategy to determine the solution. We kind of reasoned our way through it earlier, but let's see if we can actually write some equations and use algebra to solve these. So what do we have here? Let's write the system, right? That's the first thing we've got to do. Let's write the system that represents the problem situation. And you're going to use X to represent the female members of the group and use Y to represent the male members of the group. So remember that the total members of the group is 35 and that the difference between female and male members is 34. So see if you can use that information to give me two equations. Go ahead and hit pause, see if you can come up with those equations, and then hit play when you're ready to check your work. So we said female group members, hang on, I want my pen. Female group members were X, male group members were Y. And we said that together, the total, so if I added those guys together, I should have 324 people. Dun, 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 hooray. So that was nice. And we said we could come up with another equation because of this little line. We said that the female group members outnumber males by 34. So the difference between females and males was 34. And you guys know what difference means. Difference means you got to subtract them. And look at that. We have two equations. We can solve these. Now, last time we were solving these by graphing them, right? We would graph them. We'd look for where the lines intersected. And we've also been solving them by substituting, right? We're like, oh, they're both equal to Y, so they should be equal to each other. And we substituted in and solved it. There's other ways. So Chloe and Mara used different strategies to solve the system of equations in a similar way. So here you can see we have Chloe's way, and you're going to analyze each of these. You're going to write down what you notice that they did, all right? So I can use so Chloe said, you know what? I can use the substitution method for this. So what she did is she got the X all alone. You can see she took the X, she added Y to both sides. So now she knows that X equals Y plus 34. And then she took that Y plus 34 and she substituted it in for X. So instead of X, she put in Y plus 34 plus Y equals 324. And from here, she had to work it out, right? Y plus Y is 2Y plus 34 equals 324. Subtract 34 from both sides. So now 2Y equals 290, and then you divide both sides by 2, and she figured out that Y was 145. Now, once she knew that Y was 145, she could take it and she could plug it back into the original equation for Y. So instead of X plus Y equals 324, she could do 100. Oh, actually, she didn't plug it in there. Oh, I take it back. Hang on. She plugged it in here. So she took that Y and she plugged it in right there because X equals Y plus 34. So X equals 145 plus 34. So X equals 179. And that matches with what we managed to reason out earlier, that we kind of used our own logic and thinking through it to figure out that 179, there would be 179 females and 145 males. But here's what's interesting. So this is what we call the substitution method. She got a variable all alone. She plugged it in and worked it out. But Mara used a very different method that actually had a lot less work. Check it out. Mara said, you know what? You can eliminate one of the quantities by adding the two equations together. So she added her equations together. And when she did that, X plus X gives us 2X, but a positive Y and a minus Y, those guys canceled out. And it equals 3, and of course we have to add these together as well. 324 plus 34 is 358. She divided both sides by 2 and found out that sure enough, there were 179 female members. So she took that number, she plugged it in for X plus Y equals 324. So 179 plus Y equals 324, and subtract 179. And she found out that there were 145 male members, which is what Chloe got as well. But it's a very different technique. Can you explain why each student is correct, why both of these ways worked? Go ahead and hit pause, jot down your thoughts here on number 2. Wow, that's loud. Go ahead and hit pause, jot down your thoughts on number 2 on why Chloe is all right and why Mara is all right, and then hit play when you're ready to keep the discussion going. So Chloe's correct, and they got the same answer, right? They got the same answer. Chloe's correct because substitution is totally a thing we do in math all the time. Substituting an equivalent expression for X in one equation, notice how she substituted for X, and it resulted in an equation in one variable. It resulted in an equation with only Y's, and we can easily solve that. But Mara's method, and of course, once she found Y, then she can substitute Y into one of the original equations to find X. But Mara's method was also correct because the Y variables, now we've used this word, we use this word in the warm-up, right? We use this word in the warm-up. The Y variables have coefficients that are additive inverses. Remember, that was code for opposites. Notice that's a positive one, and it doesn't have a 1 in front of it. We could put a 1 in front of it, but this has a coefficient of a positive 1, and this Y has a coefficient of a negative 1. They're opposites or additive inverses. Your book really likes the word additive inverses, but you know that means opposites. So because those coefficients were additive inverses, when equations were added together, the Y variables are eliminated from the equation, and that results in us having an equation in one variable, X, which we can easily solve because there's only X's left, right? And then, of course, once we found X, we substituted it into one of the original equations so that we could calculate the value of Y. So Mara's method is also interesting, and it worked so well because those two Y's had coefficients that were additive inverses. They were opposites of each other. So that's why Mara's method of eliminating worked so well, because you added them together and it killed off one of the variables. It's kind of freaking awesome. And I think that kind of answered question number 3. Not quite. So looking at the structure of our system, so here's our system, taking a look at the structure of the system, what is it about this structure that made Mara's strategy so efficient? Like her strategy was way faster than Chloe's, right? What is it that you notice about the structure of these that made it so efficient and work so well? Hit pause, jot down what you notice, and then hit play when you're ready to check. So I noticed 2 major things. The first thing I noticed is that both of these guys were in standard form. So apparently Mara's strategy of eliminating one of the variables works best when you've got equations in standard form. And of course, the other thing was that you had a set of variables that were additive inverses, right? We had 2 coefficients that were additive inverses. So if I notice that 2 variables are have coefficients that are opposites of each other, that are additive inverses, and I notice that my equations in my system are in standard form, then it turns out this method that Mary used of adding her equations together to eliminate one of the variables works great. Like, it works really well. Very efficient. We already found the solution to the linear system, but it does say we want you to write the solution as an ordered pair. Okay, so write your solution as an ordered pair. And then, of course, you've got numbers, but tell me what the numbers are. Interpret this solution in terms of the problem situation. Go ahead and hit pause, write it down, hit play when you're ready to keep going. So my X was 179. Like we found that Chloe and Mara found this earlier. The X was 179, and she found that they both found that Y was 145. So that means as an ordered pair, we put parentheses around it, comma in the middle, right? 179, comma 145. So there it is as an ordered pair. Beautiful. But we're also asked to interpret the solution. Well, remember what all this was. This was about how many guys and how many gals are in the group, right? And we said that we found out there are 179 females and 145 males in the Comic Gurus group on this social media site. Good job. So this cool method that Mary used, I'm not going to deny, it's my favorite method. Some teachers call it the elimination method because you're literally like eliminating a variable. But the actual name of this method is the linear combinations method. So the algebraic method used by Mara to solve the linear system is called the linear combinations method. And so this is in bold. It's clearly an important key term that you need to know. So don't freak out when you see linear combinations method. That just means you're going to make sure your equations are in standard form and add them together, right? So this method, this linear combinations method, is a process used to solve a system of equations by adding the two equations together, hoping that one of them will die off so you can end up or result in an equation in one variable. And you can then determine the value of that variable and use it to plug in and determine the value of the other variable. So I really like the linear combinations method. It's definitely one of my favorites. I'm not going to deny that. I guess I'm not supposed to have favorites. I totally have favorites. So I would like you to use the linear combinations method to solve each of these. We've got several of them. We've got several of them here. We're on page 176. I want to make sure I'm there in my book too, not just on my screen. Hey. So question number 5, you've got 2 of these, 5A and 5B. I can only fit one at a time on my screen, but I would like you to use that linear combinations method to solve both of these problems. Hit pause, work them out, and then hit play when you're ready to check your work. All right, so linear combinations method says I need to take these 2 equations. And I need to add them together. I'm going to use another color just to distinguish a little bit better. So I'm going to add them together. They're in standard form. I can see I've got a couple of things that are opposites. So sure enough, I've got a plus y and a minus y, all this stuff. Let's add everybody up. So negative 4x plus a negative 2x, that gives us negative 6x. Y plus a negative y, oh, those guys actually cancel out, which is wonderful and why we did what we did, right? That was the whole point of this. And of course, 10 plus a negative 1, 10 minus 1, that is 9. Ooh, so good. So let's get our x alone. Now I just have an x. Now it's easy to solve because there's only an x left. So we'll divide both sides by 6. Oh, sorry, that's a negative 6. Oh my goodness, take it all with you. So those cancel out. That's why we did it. I almost forgot to take my negative with me. Oh my gosh. So I get x equals, that. I don't want to write it as negative 9/6. You can simplify it down if you like, right? 3 goes into both of these. So you can write it as negative 3/2. If you want to grab a calculator and divide it out, negative 3 divided by 2, I believe you get negative 1.5. So you have a few options, a few different ways of writing this, and that's okay. The only thing is that only gives us x. We still have to find y. So now that I have my x, let's take it and plug it in. I don't care which equation you plug it into. I'm just going to use the top one because it seems convenient. Ooh, making weird marks in places. So I'm just going to use the top equation. So negative 4x plus, and of course, instead of y, or pardon me, I'm putting it in the wrong place. Oh my gosh, don't listen to me. Do listen to me. I make mistakes too. You guys just get to watch it. Isn't it fun? So we're going to take this x and it equals negative 1.5. We're going to plug in for x. Sorry about that. It does say x equals negative 1.5. So we'll plug that in. So I have negative 4 times, and I'm trying to use different colors to make it easier to see what I'm doing, negative 1.5. And we still have plus y, and it still equals 10. And my colors are going all crazy now. Sorry about that. I thought I had it all down. I don't. If you multiply these together, negative 4 times a negative 1.5 gives us a positive 6. You're welcome to use a calculator. I won't judge you for it. And we got to get that y all alone. Just a y left, so I got a minus 6. Death and destruction everywhere. So it looks like we get y equals 4. Don't forget, our answer is an ordered pair. It is a point where these lines are going to meet, right? So let's write our answer as an ordered pair. X comes first, so negative 1.5, comma, my y coordinate, which is 4. Don't forget to put your parentheses around it. So pretty. There's our solution. Yay. Oh, I've got all kinds of mess back here. Watch out. What about this one? Did you freak out because you saw fractions? I hope you didn't freak out just because you saw fractions. I hope you're like, psh, whatever, dude. These guys are still opposites. They are still additive inverses. So I don't really care that these are both negative. It just doesn't matter that much to me because the truth is I'm about to add these equations and make them all go away anyway, right? Right. So let's add our equations together. And of course, a negative 1/2 plus 1/2, well, those are going to cancel out. Goodbye, which is nice. That's kind of what we wanted. That was the point of this. 5y plus, let's think of that as a 1y. 5y plus 1y is 6y. And a negative 6 plus a negative 6 is a negative 12. Well, now it's easy to solve for y. We'll divide by 6 on both sides. Choo. And we find out that negative 12 divided by 6 is a negative 2. Now, of course, I only have half of my answer, right? I still need to know what x is. So this is great. Like, I have y. That's great. That's wonderful. But now we need to take this y equals and substitute it in. I don't care which equation you substitute it into. It doesn't matter to me. So I'm just going to substitute it into that guy because it looks fine. So I'm going to substitute it in here. So this means I have 1/2 x plus a negative 2 equals negative 6. So I actually have 1/2 x minus 2 equals negative 6. So I guess I need to add 2 to both sides, right? Get that out of the way. So I have 1/2 x equals, negative 6 plus 2, that's a negative 4. Be careful, be careful, be careful. Please watch out. Remember how you get rid of a 1/2? Remember how we can multiply by the reciprocal? Remember that the reciprocal of 1/2 is just 2 over 1, also known as 2. So I'm just going to multiply both sides by 2. And that makes things so much better. Those will cancel out. And I have x equals negative 8. Oh, don't forget, we have to write our answer as an ordered pair. Please remember that the x goes first. So negative 8, comma, negative 2 for our y coordinate. And there's our solution. Woo! I really like this elimination method. I like this. I do. I like that I can add stuff together and things die off and suddenly it's so much easier to work out. I love that. All right. All right. So let's go a little bit further. So we've been using additive inverses to combine our linear systems, right? Add them together. And because we have additive inverses, we have opposites on our coefficients, it gets rid of one of our variables, makes it really easy to solve. So in the system of equations from this last activity, one of the variables in both equations had coefficients that were additive inverses, which was very convenient. But you know that's not always going to happen, right? So what if a system doesn't have variables that are additive inverses? Right? Because, I mean, that happens. You're not always going to have opposites. So let's use the strategy of linear combinations to solve other systems, even if that doesn't happen. So the general rule is this. So right here, I've got this lovely system of equations, and it is a very lovely system of equations, but you'll notice no additive inverses. 7 and 4, they are not opposites. 2, and like I said, if you want, you can put a 1 in front of it. 2 and 1, they are not opposites. This is a problem. So if I were to add them right away, nothing would cancel out. However, you guys know the multiplication property of equality. You know that if you multiply by something on one side, you can do it to the other, and it's okay. You're just rewriting the equation. You're just rewriting the equation. So here's the deal. I don't want this to be a 1. I want it to be a -2, because if it's a -2, it's the opposite of this guy. It's the additive inverse, right? That if I add them together, I'll get 0. That's what I'm going for. So I want to multiply this by -2, but you know the rule. I can't just do it to this guy. I have to do it to everybody. So I have to multiply the entire side by -2, and if you do it to one side, you've got to do it to the other. So I have to multiply the other side by -2 as well. So for the second equation, we're going to multiply both sides deliberately with a -2. And it's not just any random number we're picking. We're picking a number that's going to create additive inverses for our y variable. All right, so it's not random. Of course, you guys know that you do have to distribute. You know how that works, all of that good stuff. So -2 times 4x is -8x. -2 times y is -2y. And -2 times 15 is -30. And now, if we keep our original equation and we now take our new y equation, now we have additive inverses for our y values. Isn't that nice? So now I can add together my equations. 7x plus a -8x is -x, -1x if you'd like. Do you want to put a 1 on it? Would that make you feel better? -1x. Oopsie. And of course, 2y minus 2y, those will cancel out. 24 minus 30 is a -6. And last but not least, you can divide both sides by a -1, and you find out that x is 6. And of course, now that we know what x is, we can substitute the value of x into one of the equations to determine the value for y. I don't care which equation you pick. Pick an equation, any equation. Let's just use the first one. It sounds good. So instead of 7x plus 2y equals 24, we'll plug in our 6. We'll say 7 times 6 plus 2y equals 24. Of course, 7 times 6 is 42. So 42 plus 2y equals 24. And we can subtract 42 on both sides. That dies. So we end up with 24 minus 42 is -18. 2y equals -18 means we have to divide both sides by 2. And we get that y equals -9. And of course, we have to write our solution as an ordered pair. So 6 is our x coordinate, it goes first. -9 is our y coordinate, it goes second. Hooray. So if we were to graph these two equations, that would be the magical place where they meet up. What? So magical. All right. So if I don't have coefficients that are additive inverses, I can make it have additive inverses, right? Like I can make it do what I want it to do. So in this example that we just worked out, only one equation had to be rewritten, right? We only rewrote the second equation to solve using the linear combinations method. Why did we only have to deal with the second equation? Jot down your thoughts on that. And then hit play when you're ready. So hit pause, jot down your thoughts. Hit play when you're ready to keep the discussion going. So I only needed to deal with the second equation because that's all I needed to get my additive inverses, right? If you multiply that 4x plus y equals 15 by a -2, then the coefficients of your y terms will be additive inverses. So we only rewrote the second equation, multiplying everything by that -2 to get those additive inverses, right? We wanted them to be opposites. But sometimes it's not that simple. Sometimes it's just not that simple. So now let's consider, sorry, that's bothering me. Is that bothering you? That's bothering me the way it's written. I want to fix that. Sorry, it bothers me. I want it to be pretty. There, is that better? That's prettier, huh? It is. All right, sorry. I like things to look nice. So now let's consider a system where we need to rewrite both equations. So again, I have a system of equations. 4 and 5, they are not additive inverses. 2 and 3, those are not additive inverses. It's just not going to get the job done. So what we've done is we're going to change both of them. Last time, because we had a naked variable, well, so to speak, but like we just had a y with a coefficient of 1, it meant we only had to rewrite that equation to get the additive inverses. But that's not going to work here. I need to change both of these in order to get what I want. So I'm going to look at these guys right here. Come back now, come back now. I'm going to look at these guys right here. A 2y and a 3y. Well, that means if I made one of these a 6 and one of these a negative 6, we could make it happen, right? Because I can multiply 2 by something to get 6. I can multiply 3 by something to get negative 6. So I'm actually using the least common multiple of these two coefficients, right? I know that 2 and 3 both go into 6. So let's multiply this whole top equation by a positive 3 just to make sure that that's going to become 6, right? We're just trying to make sure that becomes 6. And then we'll multiply the second equation by a negative 2. Notice it's a negative, so that this guy can become a negative 6, right? Because that'll make that guy positive 6, that'll make that guy negative 6, and then we'll have additive inverses. So we actually have to multiply both equations by some constant number that's going to make sure that our coefficients are additive inverses, all right? This isn't the only way we could have done it. We also could have dealt with the x's, but I like to kill off y's. What can I say? Why? Because I can. And of course, at this point, we do need to distribute. So 3 times 4x is 12x, 3 times 2y is 6y, and 3 times 3 is 9. And we have to do it again over here. Negative 2 times 5x is negative 10x. Negative 2 times 3y is negative 6y, just like we wanted. And of course, negative 2 times 4 is negative 8. And look at that. We now have additive inverses. Yeah. So here's what I would like you to do. Finish it. I would like you to find the solution of this linear system. We got you started. All right, now we got our additive inverses. We can make this work out for us. Go ahead and hit pause. Add together your equations and find your solutions for x and y, and then hit play when you're ready to check your work. All right, did you add your equations together? I did. Add my equations together. So 12x minus 10x is 2x. 6y minus 6y, well, that's gone, which is why we did it, haha. And then, of course, 9 minus 8 is 1. We do need to finish this bad boy off, so let's go ahead and divide both sides by 2. Look how fast this was. We get x equals 1/2. You can do a 0.5 if you like. If it makes you feel better, that's fine. But yeah, except we're not all the way there. So this was quick, this was easy, but we need to figure out what y is. So pick an equation, any equation, I don't care, pick one and stick in your 1/2. I'm gonna use this guy because why not? So I'm gonna do 12 times 1/2. So I'm plugging in my 1/2. Plus 6y equals 9. I'm also going to point out that you could have used one of the original equations as well. It actually doesn't matter. Pick any one that you like. It'll work. It'll work. Of course, 12 times 1/2. Well, half of 12 is 6. So that's easy enough. Worked out. Next step. Let's subtract 6 on both sides. Those cancel, which is why we did it, after all. We have 6y equals 3. Oh, we got to divide both sides by 6. So that cancels again. That's why we did it. And we get y equals, now I don't want to write 3, 6. I know I can simplify that, right? I can divide both of those by 3. 3 divided by 3 is 1. 6 divided by 3 is 2. Oh, I got 1/2 for y as well. What? So it turns out my solution written as an ordered pair, x coordinate first is 1/2, comma my y coordinate, which is also 1/2, so that's convenient. Woo! And here you were so worried about fractions. No big deal. Beautiful work. Nicely done, indeed. Let's get our thing on. Go. I mentioned that there was another way of doing this, that we could have gotten rid of the x's instead of the y's, that we could have created additive inverses with our x's. How could you have done that? Hit pause, take a look at the original equations, hit pause, jot down your thoughts on that, and then hit play when you're ready to check your work. So I noticed that the x's had coefficients of 4 and 5. And I thought, well, the least common multiple would be 20. So I thought, all right, if I want my x's to be opposites, then I can take that first equation, that 4x plus 2y equals 3, and multiply by 5, right? Because that would give me a 20x. And then the second equation, that 5x plus 3y equals 4, I don't want to multiply by 4. I actually want to multiply by -4, because that will create a -20, and that would help me out, right? This would mean my coefficients of x would then be additive inverses, right? This guy would be a +20, and this guy would become a -20. And of course, there would be a whole ton of work, but we would be able to solve for y and get y alone. And then once we found y was 1/2, we already knew y was 1/2. But once we found that, of course, we could substitute it back into one of the equations and find our x, which we already knew was 1/2. We already got the answer. But so this is another way you could have done it. You could have multiplied the top equation by 5, could have multiplied everything in the bottom equation by a -4. You just would have found y first instead of x, but it still would have worked. Still would have worked. So what I would like you to do, let's take a look at these problems. We're on number 4 over on page 178. There's actually a whole bunch of these problems, But I would like you, we're not solving the whole problem. You're not solving the whole problem. But for A, B, and C, and again, I can only fit one at a time. For A, B, and C, can you just describe for me the first step? Remember, we're trying to get additive inverses. We're trying to come up with additive inverses by rewriting our equations, by multiplying an equation or both equations by something. So can you take a look at A, B, and C and just write down the first step? You're not going to solve it all the way. Just write down the first step that you would need to be able to use the linear combinations variable and just identify what variable that's going to help you find. Go ahead and hit pause. Write it down for A, B, and C, and then hit play when you're ready to check your work. I noticed something on this one. So part A, I noticed something. I noticed that these were both 2y. So I just needed one of these guys to be negative. I just need one of these equations to be -2, right? So here's what I decided. And again, this isn't the only way you could have done it to the top equation, but I'm going to multiply that second equation by a -1. Because if I multiply everything here by a -1, that will create additive inverses, make the y's go away so that my resulting equation will help me find x. It'll leave me the x. It'll get rid of the y's and leave the x. Again, you could have decided to multiply the top equation by a -1. That would have worked as well. For this one, I noticed a lonely x, and I thought, oh, well, then I can just multiply the top equation by a -5, because that's the opposite of 5. It's the additive inverse of 5. So fine, you can multiply that first equation by a -5. So when you add your equations, it's going to get rid of your x's and you'll be able to determine your y value. C was trickier. C was trickier, and that's okay. You may have used a different method than I did. I chose to get rid of the x's. If you chose to get rid of the y's, that's fine. You just would have had a slightly different answer than what I'm about to give. So I thought, all right, I'm going to get rid of the x's. So I'm going to multiply my top equation by a -3, and I'm going to multiply my second equation by a +4. And that way my x's will cancel out, and I'll be able to determine the y value. It's not the only way, but it's a way. It's fine. So along these same lines, for question number 5, you're not going to solve these. I want you to tell me how you would rewrite these equations, these systems of equations, or maybe you don't need to rewrite these equations, I'm not sure. But I'd like you to analyze each of these systems on number 5, A through E. And it's kind of like what we did with 4, what's your first step? Tell me, how would you rewrite these systems to solve for one variable? Go ahead and hit pause. Tell me what you would do to rewrite these and why you would do it, and then hit play when you're ready to check your work. So for A, I wouldn't rewrite them. I wouldn't rewrite them for A because check it out. I already have additive inverses. The coefficients on X are already additive inverses. I don't need to rewrite it. It's already going to work beautifully if I do my linear combinations method. So yeah, for A, I wouldn't rewrite either equation. It's already set to go, isn't it? For B, I looked at it and I thought, ooh, naked y, naked y. So if I make it the opposite of 3, I can make this work. So I wouldn't rewrite the first equation. I would actually rewrite the second equation. I would multiply that second equation by a -3, right? So then I could add the equations, kills off the y's, and I could figure out what my x value is. Yeah. Oh, yeah, that's way better. For C, it started to get trickier. I looked at this and I was like, all right, I'm going to have to rewrite both equations, right? There's no way around it. I'm going to have to rewrite both equations. So I thought to myself, well, let's get rid of the x's. I can multiply this by a -2. And if I multiply that guy by a 3, then that means this would be a -6. This would be a +6. And it would cancel out my x's so that I get a resultant equation that would let me find the y value. Yeah. Not the only way of doing this. You could have chosen another method, but this is just the one I chose. Oh, look, naked y. You know what to do here. The only thing is this one got weird because I did decide, okay, I'm going to multiply the second equation by a -3, but I realized something. That would give me a -6x, a -3y, and a -3. So it actually kills off all of my variables. Oh no, oh no, oh no. And 0 does not equal -3. Oh no, that's no good. So I did multiply the second equation by -3 to add the equations, but I couldn't find x because x died. And I ended up with a false statement. Well, that was lame. Oh, and this one as well. I noticed a naked x. I saw the naked x and I thought, oh, I'm going to multiply that by -2. So I decided to multiply the first equation by -2, but then I realized something. If I did that, -2x and 2x cancels out, -4y and 4y cancel out. Whoa, 12 and a -12 cancel out, and I end up with 0 equals 0. Oh my gosh. So yeah, I multiplied the first equation by -2, but I noticed that again, when I added my equations together, I eliminated both x and y. But this time I ended up with a true statement with 0 equals 0. Very interesting, isn't it? All right, guys, as always, I hope you found this useful. I hope you found this helpful. If you have questions or concerns, please talk to me. Talk to me during class. Talk to me after class. Come see me during office hours. I'm around, and I'll see you later. Bye.